Hello everyone, welcome back to the 2026 AMC 8 problems. Today we'll be discussing problems 23 through 25. These are the last three problems, so they'll be definitely the hardest. So let's just get into it. Lakshmi has 5 round coins of diameter 4 centimeters. She arranges the coins in 2 rows on the tabletop, as shown below, and wraps an elastic band tightly around them. In centimeters, what will be the length of the band? So this problem, we can divide this problem into several smaller problems. So if we connect the centers of these 5 circles with lines like this, we actually get that these triangles here are equilateral triangles, and diameter 4 means radius 2, so these are 2, 2. So these are equilateral triangles of side length 4. You can't see this. Okay, so this is a dot right here. It's another dot. This is tangent. This line is tangent to these circles at this point. So these angles are right angles, which means these are this is a rectangle, and the same thing can be done for this, and here. So these have side length 4. So this is 4, this is 4, this is 4, this is 4, and this is 4. And these are all the straight lines contained in the rubber band. So there are 1, 2, 3, 4, 5 straight lines, which means this contributes a total of 20 centimeters. And if you look at the answer choices, each of them have a plus 20 at the end, so we kind of tell we're in the correct direction. All right, so now for the curved surface. Let's look at this one. Let's look at this one and this one. So this is 60 degrees. This is also 60. And actually, this full thing is a 120 degree angle. So these two are right angles. Minus a 120 means that this is a 60 degree angle. The same thing can be done for this bottom one to show that this is 120. So these two arcs add up to 180 degrees. So these two are a half of a circle. And you can do the same thing for this and this. All these also add up to 180, which means the curved section is just a full circle with radius 2. And the circumference of a circle is just 2 pi r. R is 2, which means this is just 4 pi. Adding this to the 20 right here gives 4 pi plus 20. So the answer is C. All right, next, problem 24. The notation n factorial is defined as a product of the first n integers. Define the superfactorial of a positive number, denoted n to the factorial power, to be the product of the factorials of the first n integers. For example, this 3 factorial equals 12. How many factors of 7 appear in the prime factorization of 51 superfactorial? For this, it's easy to just write some things out. So by the definition, 51 to the factorial equals 51 factorial times 50 factorial times 49 factorial, and so on until 1 factorial. For this, I like to just list these numbers out 59 times 50 times 49 into 1. Yeah, and then 50 factorial is similar thing into 1. 49. So you can kind of see a pattern here. I'll just write this 2 here for completion. This goes to here, and 1 is this, and the 2 here is 2 times 1. So if you notice, like this, if you notice, this makes a triangle with a triangle of numbers where there are 51 ones, there's 51 ones, 52s, 49 threes, and so on until there are 3 of these, 2 and 1. So now that we've separated these, we can figure out how many factors of 7 there are. So we only care about the numbers that are divisible by 7. Those are 7, 14, into 49. The odd one out here is 49 because this is just 7 squared, so it contributes 2 factors of 7 to it. So let's find the number of 7s and 14 and so on. We know that there's 3 49s right here. To find the number of 7s, we take 51 right here, and 1 is 6 below 7. So we subtract 6 from 51. That would be 45. And every time you go down, you add or subtract a 7 to it. So you have 45, 38, 31, 24, 17, 10, and 3. So we want to find the sum of this plus 3 times 2 because there are 7 factors. There are 2 factors of 7 in each 49. So the sum of an arithmetic sequence, this is clearly an arithmetic sequence because it has a common difference of 7. You take the middle number. There's an odd number. There's an even number of terms here. So we take the average here, 31 plus 24 over 2 equals 55 over 2. And then you multiply that by the number of terms, which is 6. This becomes 3 equals 165. Add the 6 to it, and you get 171. So the answer is E. All right, problem 25. In an equal angular hexagon, all interior angles measure 120 degrees. An example of such a hexagon with side lengths 2, 3, 1, 3, 2, 2 is shown below, inscribed in equilateral triangle ABC. Consider all equiangular hexagons with positive integer side lengths that can be inscribed in ABC with all 6 vertices on the sides of the triangle. What's the total number of hexagons? So they cannot be rotated or reflected. So looking at the answer choices, these are very small numbers, so there's not a lot, which makes me think you can count them manually. So let's just get a drawing here. We have, so this hexagon is actually just a hexagon with 3 of these equilateral triangles here missing. That's probably a better way to think about that. So let's label these side lengths A, B, and C. This is not a good C. This side length 6. So this is going to be 6 minus A minus B, 6 minus B minus C, and 6 minus C minus A. So those are the sides of the hexagon. For each, I believe for each choice of A, B, and C, you get a different hexagon. So we can just find the number of A's, B's, and C's there are. Once again, the rotations and reflections are not the same. So we pretty much want to find all ordered pairs of A, B, and C that work unordered. So like that. We also know that they're positive integer side lengths, which means each of these pairs, 6 minus A minus B, is at least 1. We do some algebra, so we get A plus B is less than or equal to 5. And that makes sense because otherwise these points would meet at one point here, and it would just be like this. That wouldn't be a hexagon. And the same goes for these other pairs. So a way to count this, first of all, A, B, and C are also positive. A good way to count this is to case work on some constraint. So let's just say that A is greater than B is greater than C, because it's unordered, doesn't matter. Let's just say that casework A equals 1. Let's just list a bunch of these down. So we have 1, 1, 1, 1, 1, 2, 1, 2, 2, 1, 2, 3. For each of these, we have to make sure that they actually work. So, for example, 1, 3, 3 would not work because 3 plus 3 is greater than 5. 1, 1, 4 also works. Oh, I missed 1, 1, 3. Great job. I believe that is all. There's no more for B equals 1. There's no more for B equals 2. C equals 3 is impossible. B equals 3 is impossible. Yeah, I believe that is all for A equals 1. So let's try A equals 2 now. First of all, 2, 2, 2 works. 2, 2, 3 works. 2, 2, 4 does not work because 2 plus 4. 2, 3, 3 does not work because 3 plus 3. So I believe that's all. And A equals 3, that doesn't work. Smallest value is 3, 3, which already is greater than 6. So I think this is all. If we didn't overcount, then there should be 6 here plus 2 here equals 8. So the answer is E, 8. All right, that's the end of the AMC 8 2026. In the future, I think I'll be doing more past AMC 8 questions. Maybe I'll switch to something harder like AMC 10. But I'll see you guys later.